Okay, so let's go through the practice final. So, 12 problems. Problem number 1. I should have my solutions on me, actually. I'll just, yeah, good. Problem number 1, we have phi equals this arc cosine plus arc tangent, and we want to find the exact values, sine of phi and cosine of phi. And then after that, we'll want to determine the quadrant. Right, so the way to do this, well, let's write out what happens when we try to take sine of this. Let's see what this expression becomes. So sine of this thing of two terms, arc cosine of -3/5 plus arc tangent of -5/12. Right, so now that you see it in this format, hopefully this reminds you of a homework problem where we had to use, I guess this would be the sum formula for sine. So, and there was also something that I sort of did to simplify the working through of it, which is to sort of abstractize some of the expressions here. I'm going to try to do that here. So let's call this angle alpha and this beta. See, what happens is that the inverse trig functions, the input is a ratio of sides, the output is an angle. So these are actually two angles. That's kind of the type of units that you have here. And so now this is sine of alpha plus beta. If you don't remember the formulas, well, we can, they are on the formula sheet. I do happen to remember, but I'm going to just point them out. So that would be sine of alpha plus beta, which is going to be this rule here. Right, take the top signs. So it's going to be sine alpha cosine beta plus sine beta cosine alpha. So we can go ahead and use that. Okay, so it's going to be sine of, I'm just going to write it and then replace back what alpha and beta are. Sine beta cosine alpha. Okay. Okay, now we replace back and we see what happens. Sine of alpha, now alpha is arc cosine, inverse cosine of -3/5. Cosine of beta is cosine of arc tangent of -5/12 plus sine of beta, beta is arctangent of -5/12, and cosine of alpha, alpha is arc cosine of -3/5. So this is actually the expression that we end up getting, and we want to simplify this. So now you see these trig of inverse trig sub-expressions. So that should remind you of a part of the formula sheet where we have those sets of formulas, and these are the 18 formulas, right? This right here, trig functions of inverses, and so you've got a block of 18 formulas right there. So let's take a look. Sine of arc cosine is going to be this expression. We have x is this -3/5, so I'm just going to well, if I first just replace using the formula, maybe that is a bit better on showing the grader what we're doing. So if I write it like this without actually taking that square, then it shows me what the formula is that I'm applying. Cosine of arctangent, let's see. Cosine of arctangent is this 1/1 plus x squared. Okay. Oops. Wait, is 1 outside the square root? Yeah, it is. Okay. 1/1 plus x squared, and then plus sine of arctangent. Sine of arctangent is x over. Okay. X over. Oh, I shouldn't put x there. Let me think. 1 plus x squared Um, hmm. I don't want to put x unless I can actually simplify the expressions. The problem is that the values I have to also be careful about, because if I want it to be like that, this will be x and this will be y, so these will be y's. Okay, well let's try it out just to see what happens. Okay, and because I didn't do it this way, I actually used the actual values. So um, hmm. So this one would be x, and this one would be y, because this is x, and this is y, and this is y, and this is x. We can see whether or not the algebra simplifies. I'm pretty sure it doesn't, but let's just do it to check. So cosine of arc cosine, you just kind of know that it cancels, or you can find it. Cosine of arc cosine just cancels and gives you back the original variable. Right, so if we didn't use the actual numbers that were given to us, this would be the expression that we would deal with. And okay, well maybe it's fine. Let's see, because there is a common denominator. I see that, and I can add these things together. So square root 1 minus x squared plus x times y all over the same denominator of 1 plus y squared. Right, now we would replace x and y with what is given. So x is negative 3 over 5, so this would be 1 minus, let's square that, 9 over 25. And then plus negative 3 over 5 times negative 5 over 12. Okay, all over the square root of 1 plus y squared, so that's going to be 25 over 144 when I square the negative 5 over 12. All right, and you see there's, we can cancel the 5's there, the negatives will also cancel. I'm just trying to calculate this by hand, although you certainly could try to plug this into a calculator, and it should work fine, as long as you actually plug it in correctly. The numerator here is going to be 16 over 25. Let me just write it. Whoops, 25. You do 25 minus 9, you get 16. That's in a square root, and you can see that will simplify and be 5 over 6, which I'll write in the next line. So we have plus, and then 3 and 12. I should have saw that. This will be cancel, will give me a 4, and then the negatives will cancel as well. So we end up with a lot of cancellation. We end up with 1 over 4. And then in the denominator, okay, 144 plus 25 is 169. So this is 169 over 144, all in a square root. And both of those are square numbers, so you can see that's pretty nice as well. Let's go ahead and continue simplifying. 4 over 5 plus 1 over, 1 over 4, all over 13 over 12. Okay, right. Wonder if I'm close to. What if I made a mistake? I'll check at the end. So common denominator would be 20. 16 plus 5 over 20, and then let's reciprocate this fraction. So multiply it by 12 over 13. Okay then. So I'm getting a 21, and this 12 I want to cancel. I want to simplify this. So I can cancel 4's out, so we get 5 there. Okay, that's the correct denominator. 21 times 3 is going to be 63. Yes, over 65 when you do 13 times 5. Good. That is the answer I'm expecting. So okay. We actually calculated half of part A. We also have to do cosine. All right, so let's do cosine. Cosine of phi is cosine of, and then the whole expression. The whole expression was arc cosine of -3/5 plus arctangent of -5/12. Yes. Arc cosine of -5/12. Okay, or arctangent of okay. And let's do as we did above. We call this whole thing alpha. We call this whole thing beta, and we'll see if we can simplify the expression as we work with things. I'm going to let that fraction be x and that fraction be y. Okay. Right, so now you see this is cosine of alpha plus beta, so this is another angle sum formula, which is down here somewhere. Sums and differences, yes, there we go. So cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. So we use this formula. So we have writing it without replacing anything, it's cosine alpha cosine beta minus sine alpha sine beta. Now let's go ahead and substitute in what alpha and beta are. So alpha is arc cosine of negative, well, right, we're trying to be abstract about this, so I'll just say x, and then cosine of arctangent of y minus sine of arc cosine of x times sine of arctangent of y. Do I want to put extra parentheses? That's fine. Okay. Right, so cosine of arc cosine, that just simplifies and gives you x. Cosine of arctangent, I have to check the formulas for. Let's see if I can jump to it. No, I can't. Cosine of arctangent is there. Okay. So 1 over 1 plus x squared, but our input in this case is y, so it's going to be 1 over 1 plus y squared. I think there's a square root. Is that? Okay, my computer's complaining. Hopefully everything's okay. Alright. Sine of arc cosine of x is that. Okay. Square root of 1 minus x squared. Good. And then sine of arctangent of y. Sine of arctangent of y is this one. So y over the square root of 1 minus, is it minus or plus? It's plus. Okay. Plus, I should have known. Plus y squared in a square root. Right. So this is the abstract expression. And, well, we do actually still have a common denominator, so maybe it wasn't too bad to do this. You see the square root of 1 plus y squared there, and you see an x here, and then a minus y times square root of 1 minus x squared. Okay, so we can simplify that expression algebraically, just getting into this format. And now we replace x and y with the values that we have. So x is this -3/5, y is -5/12, as before. So -3/5 minus, was it -5/12? Yeah, -5/12 times the square root, 1 minus -3/5. So let's just square that. And then divided by 1 plus -5/12 squared. So that's going to be 25/144, all in the square root. So you'll notice that these expressions you've already computed, actually, in the previous, so here and there. If you didn't notice, you can still recompute it. That's not so bad. Let's come down here, -3/5, plus, because the negatives will cancel, 5/12, and this is 16/25, which is 4/5. And then the denominator is 169 over 144. When you take the square root, it's 13 over 12. All right, and let's cancel some things out. So 5 and 5, 4 and the 4 in the 12. So we get 1/3 actually. I'll rewrite that. Maybe I'll do it like this. I'll flip this fraction also. So 12 over 13. Okay. And now let's see. Common denominator is 15. You have -9 plus 5 over 15 times 12 over 13. The most I can do is cancel the 3's out of this. 4 and 5. -9 plus 5 is -4. Yeah, so you get -16 over 65, I believe. Yes, that matches my previous calculation, so yes, I'm pretty certain that that's right. Good. Right, so that's how you do part A of number 1. And then, computer's being a bit weird. And then part B is determine the quadrant, right? So what we do is we look at the signs of the sine and cosine. So for part B, we found that the sine of phi is actually a positive value. The cosine of phi is a negative value. So that tells us sine being positive means it's the upper 2 quadrants, cosine being negative is the left 2. That isolates which quadrant we're in. We're in the second quadrant. So we're in Q2, I'll say. And I'll go ahead and box that. Right. So that was number 1. Let me grab number 2. Copy, paste. Oh, okay, that's too much. Okay, given theta in quadrant 2 with tangent theta equals -3. So that is all the information that we have about our angle. Tangent theta is equal to -3, and it's in the second quadrant. So let's draw what this would look like. Maybe we can use that. So that is an angle in the second quadrant and the representative triangle. Tangent being -3 means opposite over adjacent is like this, and this side is viewed negatively because the x-coordinate is negative, whereas the y-coordinate is positive. So we get these, and then of course we can complete the square to get the length of the hypotenuse. It's square root of 10 because 3 squared plus 1 squared, take the square root, is going to be root 10. So that's how we get the hypotenuse. Find all 6 trig functions of the double angle. All right, so it wants to use the double angle formulas, and of course, exact values. Right, so let's start by writing out sine of 2 theta, okay? And if we use the double angle formulas, which are in the formula packet, the one I would want to, actually, I don't even need to use them. Right, I forgot. This is the one. So because sine 2 theta, cosine 2 theta, and tangent 2 theta can all be written in terms of tangent, we can actually just use those formulas. We don't need to do what I was doing, which would isolate, that gives us like sine of theta and cosine of theta. So we could actually do it using these other expressions. Like I was thinking of this sine 2 alpha cosine alpha, but since we're given tangent, we can just use tangent. We don't necessarily need all of that. Okay. Right. Although, if you do it that way, you should still get the same answer. 2 tan alpha, 2 tan, I'll say theta since our problem is in terms of theta. 1 plus tan squared theta. Okay. Yeah. And then that's minus 6 over 1 plus, and then we square the negative 3, we get 9. So we get negative 6 over 10, so we get negative 3 over 5. All right, so that's one of the values. Cosine of 2 theta we also want. So that is going to be 1 minus tan squared, 1 over 1 plus tan squared. Okay. 1 minus tan squared theta over 1 plus tan squared theta. 1 minus negative 3 squared, so that's the squaring negative 3 gives us 9. We still have the negative from this subtraction. And then 1 plus 9, so we get negative 8 over 10, so we get negative 4 over 5. Okay. And then lastly, or actually, I have to calculate all 6. So, but this is the last one that I need to compute. The others I can just reciprocate. So for tangent, I would just do sine over cosine, right? So just write it, tell the grader what you're doing. I'm taking sine, I'm dividing by cosine. That's going to give me, and then I could just do the mental arithmetic, right? So we flip this, the 5's will cancel, and the negatives will cancel. We're left with 3 over 4. I'm going to now box these results. Oop, doesn't stay. Box. Oh, that's annoying. Box. Okay. And then you should put secant and cosecant, and I mean, I guess I could put it off to the side since I have the space. Otherwise, I guess you would put it below. Cosecant is a reciprocal, and it's going to be negative 5 over 3. Secant is reciprocal of cosine, and that's going to be negative 5 over 4. And then reciprocal of tangent is cotangent of 2 theta. That's going to be 4 over 3. Okay, we can box all of those. I'll just do that by hand because that's faster. Right. Anything else? No, that's it for this problem. Okay. I should probably also double check. Negative 3 over 5, negative 4 over 5, 3 over 4, and the reciprocals. Yes. Good. Okay. Next, number 3. Cut off the 17 there. Let me, one more. All right. Okay. Theta is between pi and 2 pi. Cosine. So this specifies an angle, and we want to find the values of sine of theta over 2 and cosine theta over 2. So we expect to use the half angle formulas. And then remember that with the half angle formulas, you've got this plus or minus that you need to disambiguate. Okay. Well, let's start by writing out the half angle formula. So sine of theta over 2 is equal to plus or minus, and then there's some square root. So we would quickly consult our formula sheet. 1 minus cosine theta over 2. 1 minus cosine theta over 2. Okay. So we do have cosine, but we can't resolve this plus or minus unless we know what quadrant our angle theta over 2 is in. Well, thankfully, we can deduce that from here, I believe. So if we divide this by 2, this triple inequality, theta over 2, and then this 180 degrees. So now this tells us it's between 90 degrees and 180, so that actually specifies for us this quadrant. So theta over 2 lives in the second quadrant. Okay, now let's label our axes, and we see that sine is positive and cosine is negative in this quadrant. Great. So we can we can tell that we actually want the positive solution for this square root. Okay, and then let's keep going. 1 minus the value for cosine given to us, so that turns into a plus 17 over 25 all over 2. Okay, which is going to be, and the square root is, or the divide by 2 is inside the square root. I should make that a little bit more clear. Okay, if I add these, 25 plus 17, 42. 42 over, and then the denominator is going to be 25 and then divided by 2 again, so that combines to be divided by 50. All in a square root. We can simplify the fraction. 21 over 25 in a square root. I'm going to drop the plus now because it's redundant. Okay, now the 25 we can pull out of the square root since that's a perfect square. So we get 1 over 5. And then the root 21. 21 is 7 times 3. We don't have any other squares in that. So this is the simplest form for this radical. Okay, so we got sine of theta over 2 now. Now let's do cosine of theta over 2. So again, we know it's plus or minus, and then there's some square root expression. Let's look at our formula sheet. So it's the same as sine, but with a plus instead of a minus. 1 plus cosine of theta over 2. Okay. And in this case, cosine is negative. We want the negative solution based on the quadrant that this theta over 2 is in. So we want the negative guy now. And then we have 1 plus, no, not plus. The cosine is negative, so it's going to be 1 minus. Okay, 1 minus 17 over 25, all over 2. Okay, and let's see what happens. So 25 minus 17, 8. 8 over 50. Because again, it becomes an 8 over 25 on top, and then divided by 2. The divide by 25 and the divide by 2 will combine to be divided by 50. And we can simplify the fraction inside. So this becomes 4 over 25. And then both of these are square, so we can actually pull both of them out. We can just simply take the square root. Okay, let's see that that matches. It does. So let's go ahead and box these two. Okay. Great. So those are the exact values. Number 4. Okay. A little bit bigger. Number 4. So we have this difference of two trig functions. Find all solutions to the equation. So I'm thinking that I need the, okay, well, it does tell me. I need the sum to product form identity. Okay. So that's this one of these guys. We see sine minus sine right here. So we're going to use this expression. Let's go ahead and do it. So maybe I'll write it in a little bit more detail. So sine of 5x. And then by using the expression, we get a 2 sine of, so I subtract, notice that u and v are always in order, right? As inputs, it's u and then plus or minus v with the trig stuff, and then inside of the re-expressed versions, it's always u plus v or u minus v. So we always are in the same order. That's kind of a nice little mental shortcut to have. All right, u minus v. So first we take the difference of these angles and then divide it by 2. So 7x minus 5x gives me 2x. Divided by 2 gives me just x. And then the other guy is going to be cosine of, and then I add the two angles. Cosine of adding the two. So 7 plus 5 is going to be 12. Divided by 2 is going to be 6. So 6x. Okay, so that is what I get when I apply the sum to product identity. And, well, this thing was equal to 0 originally, so that stays. All right, now to make this happen, we must have that either sine of x equals 0 or cosine of 6x equals 0. And we handled these two cases separately, so we may as well draw that little... I'm gonna just... Good enough. All right, sine of x equaling 0. So if we think about our unit circle, and cosine is here, sine is here, to make sine equal to 0, we want coordinates whose y value is 0. So that ends up being over on this end and over on this end of the unit circle. In other words, we would have pi and we would have 0, and then plus 2 pi k. But notice that because these are the same distance around the unit circle, we can collapse the two solutions into one solution. We can just say 0 plus pi k. We can have the full circle revolution, and that will go. So the you see that, like, for odd values of k, you land on this left one, and on even values of k, you land on the right one. And so you kind of alternate between the two when you increase your k. Okay, and so these are the possible angle values for cosine to take that will make cosine of the thing equal to 0. So this is x now. And then really, yeah, that's basically the simplest form. So x is equal to pi k. That's fine. Right, with this cosine of 6x, it's a little bit more complicated, but it's not that much more complicated. So cosine and sine, again, to make cosine equal to 0, we want the coordinates where the x coordinate is equal to 0. And that's going to be these two guys. And so one of these would be normally written as pi over 2, and the other guy would be written either as 3 pi over 2, as I like to do, or as Nagi likes to do, negative pi over 2. But, you know, these are, again, just like in this case, they are symmetric, or they're the same distance around the unit circle. So we can collapse the two solutions into one by saying pi over 2 plus pi k, rather than 2 pi k. We just have that amount of distance, and we end up jumping from one solution to the other as we increase our k. This is supposed to be equal to the angle inside of the cosine, and so that's equal to 6x. And now we solve for x. So x ends up being pi over 12 plus pi over 6k. Right, so these are the two solutions. Okay. I'm just checking. Yep, same thing. Good. Right. Next, number 5. I don't want cursor. Okay. Where's my cursor now? Ah, good. Oh, that's... Oh, that's fine. Okay, so let's try to diagram out this, what's happening in this. So Andrea and Bob are leaving a point C. They are going in different directions, different distances, and we want to find out how far apart they are afterwards. Rounding it to 3 decimal places, which makes sense because these angles are not standard or not like special angles. Okay, so let's draw where C would be. Andrea north and then 59 degrees east tells me we start off north, but then we do an angle out of about 59, so let's just say it's like here. So Andrea is going to travel this way. The angle, I guess it's called bearing angle or something, is like that. And the distance is 80 miles, and we land at Andrea's location, so I'll denote that by A. Bob goes west instead, so let's, that looks something like this, 37 degrees, and it's 70 miles. Okay, and we have this, and what we want is the distance, so diagrammatically what we want is, we want this guy that I'm drawing in blue, which is the length of that other part of the triangle. Okay, so this relates to the whole solving of a triangle. That's why that hint makes sense. And notice the situation we have. We actually have side angle side, right? We can easily figure out what that angle is. That's 37 plus 59. That's 6, 1, 5, 6, 9, 96 degrees. Okay, 96 degrees. And we have these two things. That kind of reminds me of a formula. I think there's a formula that will just give me the other side. So that's area. That's not what we want. We want the side length. Law of cosines. Yes, yes. So, yeah. So if we have two of the sides and the angle between, we can find the opposite side. That's what this is saying. And actually, I think we can just label this and see exactly what we are working with here. So this side corresponds to the side length A. This side corresponds to the side length B. And we're looking for the side length C. So that's actually going to be this first guy, this first equation. So we can go ahead and write the equation down. And then we'll have to use a calculator to actually calculate it. So we get, what do we get? C squared equals A squared plus B squared minus 2AB cosine C, I think. C being the angle, minus 2AB, yeah. Okay, great. Let me just open up my calculator. I don't know what these are. Clear. Okay. I mean, you could try to plug it in like manually and see if there's. If I remember right, there's no way to simplify this. So it's 70 squared plus 80 squared minus 2, 70, 80 cosine of the angle C. The angle C is this guy we computed, so it's 96 degrees. And then you take the square root afterwards. Yeah, that doesn't really do much of anything. Let me just make sure I'm in the right mode. So I'm in degree mode, that's good. Decimal, that's just how long the output's going to be. So we're going to need to take a square root at the end. I'll just write that SQRT for this calculator. You guys should know how to use your calculators to do the same thing. 80 squared minus 2 times 70 times 80 times cosine of 96. Okay. So that is the length I'm getting. So can I just copy and paste? No, I can't. Okay, well, C is equal to 116 point something something. 111.6723. Okay, 111.6723. Round to 3 decimal places. Yeah, whatever. Okay, miles, right? Because the problem is written in miles. So this answer, ooh, that's weird. Um, let me double check. Minus 2 times. Let me take a. Oh my gosh. I did, didn't I? Yeah, okay. I think when I first did this yesterday night, I didn't take a square root. Okay. Yeah. Okay. Yeah, so don't forget to take a square root. That's a terrible mistake. Okay. I got it this time. Okay. Right. Yeah, of course. And it makes sense as well, right? 70 and 80, that should be in the ballpark. 111 is in the ballpark. I got 12,000. I wasn't paying attention. That's fine. Okay. Number 6. Number 6. Express all angles in degrees, round to 3 decimal places, solve this triangle completely. And we're given 3 sides. Right. The way I would start this is by trying to sketch this thing. So this is a triangle, and each of the sides are about the same length. So if I okay, the way I've drawn this, I actually want this side to be A equals 5, and then this side to be like B equals 6, and this side to be C equals 7, and these are all in centimeters. So that gives me this is angle A, this is angle B, this is or CBA. That's what I meant. Right. I mean from like visual intuition, you can kind of say that this triangle is acute. Like it just in order for it to be obtuse, you really would expect to see one of the sides be maybe around double one of the other sides, or the other 2 sides, I would say. Which doesn't happen here. But then again, you can also have like a really tall like isosceles. So that's not always the case. I mean, my intuition tells me this is acute. So then, like law of sines, I'm not scared to use, but otherwise, for this case, right? This case, and I guess like okay, just in case people don't remember, like I've written down how you go through these cases. So triangle solving, this is side side side. Maybe I should add a caveat to this. My eyes. Sorry. So what I've written here is that you can use law of cosines once, and then use law of sines afterwards. Because once we use law of sines once, we end up getting one of the angles. Then we have an angle side pair, and that allows us to solve the other 2 using law of sines. The caveat here is we know that law of sines is a little bit more nuanced, right? If you don't know that your angles are acute, if they could be obtuse, then you actually have 2 solutions that you need to contend with, or you need to somehow eliminate the obtuse solution. So then, in this case, like the other alternative approach is to just use law of cosines 3 times. I'm gonna go ahead and use law of cosines 3 times just because I think it's easier to explain that. In this situation, I'm not sure it'll be that instructive to see like how we can deduce the law of sines is okay. I mean, I think it's probably overkill. I don't know if you guys would care about that. So let's just use law of cosines here. So the angle C is arc cosine of b squared plus c, or b squared, a squared plus b squared minus c squared, a squared plus c squared. Okay, yeah. A squared plus b squared minus c squared over 2ab. Yeah, 2ab. Okay. Okay. And then I would just plug this into a calculator. So arc cosine of, and then I have to be careful, make sure I parenthesize things well. So a is 5. Actually, I mean, okay, so This is where knowing how to use a calculator really helps, because I can actually set variables for this guy. B equals 6 and C equals 7. And I mean, for scientific calculators, usually they have this functionality. Definitely TI-84 has the functionality to store values into variables and then use those variables. So I'm just going to do this because it's going to make it a lot easier to see that I haven't done anything incorrectly. 2 times A times B. Okay. So I've parenthesized both the numerator and denominator just to make sure that you effectively do need both. If you're trying to like write the expression in one line instead of like writing a part of it, hitting enter, and then writing the other part. If you're just writing it in one line, you do need to have parentheses both on top and bottom of the fraction. And you end up getting this. Okay, so this is 78 point something. 4630. Okay. 4630. And this was in degrees because my calculator is in degree mode. I can go ahead and calculate b hat, a cosine, and then we just sort of permute the variables around. So it's a squared plus c squared minus b squared over 2ac. You can check that with the thing that's given. So yeah, that is indeed the correct expression. And we can go ahead and type that into our calculator. Arc cosine of c squared minus b squared over 2 times a times c, 57.1216. Okay. Did I do that right? 57.12165. All right. Extra 5 just to, extra 5 just to make myself happy. Oops. I don't know. Okay. And then a. So that would be arc cosine of, this time it's b squared plus c squared minus a squared over 2bc. Which you can check, yes, that is correct. You see, all you have to do here is like, you plus the letters that are not the angle, and then you subtract what is the angle, divide by the two sides that are not the same letter, right? So these two are not the same, these two are not the same. This thing that you're subtracting is the same. So it's like there's a pattern here. There's a bit of a symmetry going on. Okay, I need to calculate this. So arc cosine of b squared plus c squared minus a squared divided by 2 times b times c gives me 44.4. Of course, we also could have just subtracted too, but I'm gonna do this, and then I'm just going to do a sanity check and just add these and make sure I get 180. 44.4153. Okay. All right. So now just to double check ourselves. 78.4630 plus 57.12165 plus 44.4153 is really close to 180 degrees. There's some round off. So, right, we're pretty confident that this is correct. And I'll just go ahead and box this. It's kind of weird to box it like this, but okay. Number 7. Copy. Paste. Oh no. Okay. Solve this thing. We've got AC and angle A express, and this has 2 solutions, it tells you. Right. Well, it's very helpful that it tells us this. Otherwise, we would have to kind of muddle our way through. We'd have to understand what we're doing. Let's see. Did I draw something that looks anywhere near what this is? I mean, this kind of looks like 30 degrees. So I'll say that's A. And this one is like 5. And this is A. And then C. Yeah, you're just gonna have to imagine that this is 8. C is equal to 8 feet. Okay. Oh wait, no, there's 2 solutions. So, how do I want to do this? Uh, well, whatever. Let's see. Let's see. B. All right. So, mm, yeah. So what happens is that the only step that we can take is we solve for angle C, because based on the configuration of the information we're given A and the opposite A, right? We're given this side angle pair, and we need to, the only thing we can do is to figure out this other side angle pair. Then we would have two angles, we could solve for the third, and then get the side B at the end. And of course, this requires law of sines, and it requires it in the way that gives us this issue of having two possible solutions. So let's see what happens. Sine of A over A is equal to sine of angle C over C. If you remember your law of sines. If you don't, it is in the formula sheet. It's this right here. Right. So you've got this, and if we solve for what we're after, we are after the angle C. So just moving things around, I multiply C over, and that will give me C over A times sine of angle A. Then we would take the arc sine, and it's the fact that we take the arc sine that is problematic. So, oopsie. Oh, come on, don't do that. Okay, so C hat equals arc sine of this C over A sine of angle A. So when we plug this into a calculator, and yeah, I'm not going to use variables because the variables are different already at this point. We're in degrees, so we can plug 30 degrees in, fine. Arc sine of, and then C, so that's 8 divided by A, which is 5, multiplied by sine of 30 degrees. Actually, you should know what sine of 30 degrees is. It's 1/2. Why is it complaining? Arc sine. I need to use arc for this program. No. Arc sine. Okay. So it gives me an angle, 53.13 something. 1301. I'll just put an extra 2 decimals, or extra 1 decimal, I guess. So it's about this. I should say about. Okay, this is one of the solutions, right? Because arc sine, if you recall, arc sine is always going to give you this solution, a solution in the first quadrant, but you will actually have another angle whose sine value will be the same, and that's because cosine sine being the y-coordinate, you have another point on your unit circle that has the same y-coordinate, namely the reflection about this y-line. So it's going to be, so the other solution is in the second quadrant with the same y-coordinate. And to compute that angle, we would do 180 degrees minus, right? Since we're in degrees, we're doing 180 minus. If we were in radians, we'd do pi minus. So theta minus this 3.1301 degrees is going to be, I should probably still say approximately, 180 minus answer, because my calculator has answer 126.869. Oh, that's a lot of numbers. 126.86896986997. I don't know. 9 what? 989. All right, fine. 989. I'll leave it at that, I guess. Technically, you could only be accurate to like this last decimal place, but whatever. That's because when I use answer, it's actually using the entire value here. So it can be a lot more precise, my calculator, which is, it's always better to use the calculator's precision. Okay. Right. So we have two possible solutions, and then the hint is telling us that there's no way of eliminating either one of them. The normal way you'd go about trying to eliminate them is by considering the inequality, the the order relationship about the sides and angles. So here it's like it's hard to express using this, but okay, let's just go ahead and um let's just go ahead and do this. So C, we'll have two different cases. So first, if C is 53.1301 degrees, then that's going to tell us what B will be, because we know angle A is 30, we know B is what was there, so we would do 180 minus the 30 degrees, that is angle A, minus the 53.1301 degrees, that is angle C. Okay, so we would do that. 180 minus 30 minus 53.1301. Okay, so this is about 96.86, 96.8699. Okay. And then B, we would, well, to get to B, what we should do is, so in this diagram, we have A, B, and C now. I would use the law of sines, because in this usage, it's not ambiguous. I would probably stick with the pair A and A, because the angle A we know precisely. So I would use sine of A over A is equal to sine of B over B. And I would rearrange this. So this, solving for B, we multiply by B, we divide both of those over. That's going to bring an A to the numerator, and then we have sine of the angle B over sine of the angle A. Okay. And, I mean, if we wanted to be precise, or if we wanted to plug things in part way, like, we could do that, but it doesn't really help us, because this is just 1/2, so this becomes like 2. I guess I could just write it. So I'm thinking that this is sine of B is this 69.8699 degrees over sine of 30 degrees. Sine of 30 degrees is 1/2, so this is 10 times sine of 69.8699 degrees. 10 times sine of 96.8699 gives me a length of 9.9282. Okay, approximately 9.9282. I have copied that down correctly, good. And then the units are feet. Okay, so if I have this case, we would have this. And then I guess the one thing maybe to try double checking is that this case makes sense. Okay, so the way we do that is we think about the order relationship, as I said. So the way that works, the order relationship, so let's keep in back of our mind that the angle A is 30 degrees. So notice how A, B, and C, the angles, relate to each other. You have that the angle A is less than the angle C is less than the angle B. Okay, and then the fact that we know about the order relationship between sides and angles is that they have to have the same order relationship. So this means we must have that the side A and the side C and the side B are, well, the sides have the same order relationship. So we just would, the way that we would just sanity check things is that that this holds true for the sides as well, which I believe it does. Didn't do that, but yeah, let's see. So A is 5, C is 8, and B is 9.9. Okay, yeah. So that is good. So this, we see no issues with this configuration, or this possibility for this angle, this case, right? We can't eliminate this case based on this data. And usually, like, if we could eliminate cases, it would be because of a failure of this order relationship. All right. So we have this case, but remember that there's actually another case. So we kind of need to do the same thing for the other case. I'm gonna just put a little separator. So in the other case, maybe I'll say or there, or C is equal to the other angle we computed, which is over here, 126.86989, being very pedantic maybe. B. So just like before, we would calculate the angle. So in again, starting over, we were able to compute C, and then we subtract off to get B, and then we would find the side B. So we do the same steps, basically, just with a different angle. So 180 degrees, we subtract off 30, that is angle A, and then we subtract off this angle C that we are using, 989 degrees, and let's see what this is. I should say approximately. So 180 minus 30 minus 126.8699 is 23.13011 degrees. Yep. Okay. All right. And so again, we would prefer to use the A and A pair because we know the angle A precisely, whereas we don't know the angle C precisely. That would give us further round-off error. Okay, so we do the same thing, except when we substitute, we use the other angle, So again, like the 5 and divide by 30 is still going to give me a 10 in front. We still have this. But then we do a sine of the new angle B, so that's 23.13011 degrees. I'm just kind of skipping over this intermediate step here. And then we go ahead and plug in 10 times sine of 23.13011. Okay, is 3.9282. And that's probably good enough. And this is, again, measuring distance, and in this problem, it's in terms of feet. So we can go ahead and box these guys, and then we should also just think that this configuration makes sense. Just kind of sanity check that everything makes sense. So in this case, the angle C is the biggest. We have B. Angle A is 30, so actually B is smaller, right? So B is smaller than C, or than A, sorry, and then A is followed by C. So this is the order relationship of the angles in this situation. And then let's see what happens with the sides, because we should get this, otherwise the situation is problematic. So we found that B is 3.9. We know that A is 5 and C is 8. A is 5 and C is 8. So yes, actually, the sides do obey the same order relationship. So that's great. Everything checks out. Okay. Number 8. Solve this triangle, and then compute its area. Okay. Express all angles, blah, blah, blah. Okay, yeah, so the thing is, I think you actually don't need to solve fully to compute area, but for whatever reason, you're supposed to. because there's actually a formula for computing the area using I think exactly this configuration. Let me just make sure that I'm not making things up. Oh no, is it two sides and one angle? Two sides and okay, so that no, it's a different setup. I see. All right. Yeah, but normally you wouldn't need to solve the full triangle anyway. You could just solve part of it. And anyway, does this look anything like what is said here? C equals 35 degrees. Sure, that's A, fine. A equals 65 degrees. You could compute B right off the bat. And then side B is 5 centimeters. Let's go ahead and compute what angle B is. 180 minus 65 minus 35. Up 35. 80. Okay. So, I guess just to show our work, angle B is 180 minus 65 minus 35 is equal to 80. 80. Okay, then, this version of law of sines is fine because you're not taking inverse sine. That's how I'm going to justify using it. So, we have sine of B over B is equal to sine of A over A. Right, and then if we solve for what we're after, which is the side A, we get A is equal to B sine A over sine B. You see, we are not doing an inverse sine in this expression, so actually this gives us only one answer. This is the better usage of law of sines. This is the non-problematic usage of law of sines. 5 times sine of angle A is 65 divided by sine of angle B. Angle B is 80. Okay, oops. So we get 4.601, I think I saw. Yeah. And this is measuring a length, centimeters. Okay, we can then also solve for C. So again, I would rather use sine of B over B is equal to sine of C over C. And we're solving for the side length C, so we solve for this guy, we flip things around, and we get B sine of angle C over sine of angle B. And then we go ahead and plug things in. So B is 5 times sine of C is 35 divided by sine of B is 80. We get 2.9121, I think I saw. Yes. Centimeters. Okay. So we solved the whole triangle. Now to compute the area, how would that be best done? I should probably also just double check my answers. Let me just do that really quick. Yes, that was good. That was fine. I think I'm happy with that. So I guess I should check number 5. Sorry, let me just do that. Wait, what am I? Number 6. Yes. Okay. Number 8. I forgot to do the area. Yeah, don't read the problem. Make sure you solve everything. That's terrible of me. Compute the area. Forgot to do that. Okay, so well, I don't want to use Heron's formula because 2 of these sides we derived and they are not precise. So I really don't want to use Heron's formula. I would want to use the SAS formula. But that still requires 2 sides and an angle. But thankfully, all 3 angles we know precisely. So we're going to have some imprecision coming from using one of the sides. And there's no way around that. So I'll just use the first guy, I guess. So area, I don't want this different color. So area, let's say AB, what's the formula? AB sine C over 2. We know B precisely, so yeah, we just need B in there, or we would prefer B in there somewhere. So I guess just, yeah, plug it into a calculator. A is this 4.601. I mean, I see more of the decimals, but yeah, I'll just use more of the decimals because I have them right in front of me. A times, and then B is 5 times sine of C, which CIC is 35 degrees, divided by 2. Okay, so area, I got 6.5982 centimeters squared. Okay. I guess that's a reasonable enough answer. Let's go ahead and box everything. So we solved the triangle, getting these 3 values, and then we computed the area of the triangle. Okay, so that was what we were asked to do. Good. 4 more problems. Okay. Solving good area. All right. Find the exact value of all 6 trig functions of this rather big angle. Okay. So the first thing that I want to do is to reduce this angle. And I do that by subtracting off multiple copies of a revolution of the unit circle. So that's multiple copies of 360 degrees. Okay, so if we use 5 copies of 360 degrees, we wind up at 30. Okay, so this 1830 degrees is equivalent to just 30 degrees. The trig functions are not going to recognize the difference between these 2 angles. They're going to view them as the same thing. So all we do, I'm just going to parenthesize so that the grader understands, is that we subtract off 5 copies of 360 degrees. Right. Or maybe it's better to actually say it like as a full statement. So I'll say like come on. If I take 1830, subtract off 5 copies of 360, I get 30 degrees. This is my justification for these angles being equivalent for the different trig functions. So then what I would do, the problem asks us to evaluate these trig functions on this huge angle, but really we're thinking of it as evaluating on the small angle, because this is the equivalent angle. And then of course your unit circle, if you don't have it memorized, well, we have that thing there. So that's where's this? So you have to remember that pi over 6 is 30 degrees, and then you can just the trig values are written right in this column. So sine is a half, and cosine is √3 over 2, and tangent is let me fill out this line. And tangent is 1 over √3, as I like to express it. Or you could say √3 over 3, which is the more common textbook way of writing that. And then, well, for the other column, we just reciprocate. So it's a bit of a pain to write everything out in full detail, but I'll do it just this once. Secant 1830 is the same as secant of 30 is equal to 2 over root 3, and then cotangent of 1830 is cotangent of 30 is root 3. And so these are all of the values. I don't know. I'll box them vertically, I guess. Okay. All right. Number 10, copy. Oh no. Number 10. Given this angle is in the third quadrant, and we're given some information, find the exact values of the other 5 trig functions. Okay, this one is really the whole drawing what the angle looks like. So we're in the third quadrant, our angle looks like this. Representative triangle looks like this. Cosine is -1/3. Cosine is adjacent over hypotenuse, so adjacent over hypotenuse, and this side we view negatively, and because of this negative as well. So we have that, and the other side we calculate by doing 3 squared minus 1 squared, and take a square root. So we get square root of 8, which I can rewrite as 2 root 2. I just pull out the 4. By pulling it out, I take its root, and I get 2 root 2. Okay, find the exact value of the other 5. So basically we read off all of the values from this triangle. This is viewed negatively because this side is negative, because the y-coordinate is negative, right? Okay. Sine, cosine, tangent, cosecant, secant, cotangent. I like to do it like this so that I don't have to think very much about what I need and what I don't need. It's fine to be moderately redundant, right? Give the value that we're given, and -3. Oh yeah, and then of course, like if you're the kind of person that prefers all those the crazy formulas, you can do it as well that way, I believe. I forget. I guess you would take the arc cosine, and then you would just you would take the arc cosine, then you would just plug everything into these 6 formulas, and that would do the trick, I guess. But I don't like doing that, so I'm gonna do it this way. So sine is opposite over hypotenuse. Oops, 2 root 2. This reciprocate, so -3 over 2 root 2. Tangent is opposite over adjacent, so we get 2 root 2. And then reciprocal, 1 over 2 root 2. Yeah. Okay. But yeah, you could certainly plug it into these formulas. I don't think it's that bad. Yeah. Okay. 11. Identity. Identity. Verify this identity. Okay. So when we verify identities, we're not allowed to just move things around the equality sign. We want to just work with one side, work with the other side, and somehow arrive at the same expression on both sides. Secant. When I see a secant, I don't like that secant, right? I would prefer things in terms of sines, cosines, and possibly tangents. Having the reciprocal functions are a bit less convenient. So we would view this as 1 over cosine of tangent minus cosine of tangent. And that's really going to be the starting point here. Once we see this, we can then combine these two. We can actually apply this subtraction, and that will give us 1 minus cosine of t quantity squared, and then divide by cosine of t, right? We get that by we would need to take a common denominator, so we get cosine squared over cosine, then we subtract across, giving us this. So, and then once we notice this numerator, we should be reminded of the Pythagorean identity. So sine squared plus cosine squared equals 1. When you subtract over the cosine, you get sine squared. So the numerator is just sine squared of t over cosine of t. And now this is really in the format, this is really quite like similar to that. So, I mean, one thing maybe is instead of re-expressing it this way, you might just have broken this apart, so I'll just show that instead. So sine of t, and then tangent, you would think of it as sine of t over cosine of t. Okay, and then once you see this, well, yeah, these are really quite the same. So I'll just do it one more time. I'll just do one extra step, and you see that these are equal. So we verified the identity. Okay, last problem, number 12. So this covers new material than what we did in the recitation. This is what we're going to be covering next week at the time of recording. Involving taking a cube root. So, I haven't really thought about how to explain this, but with taking a cube root, what you want to do is start by expressing your complex number as a polar in polar form. You want to write the complex number in polar form, and then you use what is de Moivre's formula, because that's an easy way to calculate powers of complex numbers. So this guy, when we try to write it in polar form, we have to end up taking a cube root of, well, first I would try to visualize where this is. So this is over here. This is negative 216i. So it's on the imaginary axis, and it's a distance of 216 away from the origin, and it's in the negative direction. So when we write this in polar form, we have a radius for this, which is 216, and then we have an angle of this, which is e to the I, and then pi over, 3 pi over 2. 3 pi over 2. Or you could say negative pi over 2, because that's just different ways of writing this angle. You could, this angle versus, use a different color versus this angle. It's just the perspective of which one you want to take. I think I remember he said something about principal value. So the principal value would actually have, would actually use negative 3 pi over 2. But for our purposes, it doesn't really matter, because we actually start with like this general solution that uses multiple revolutions of the circle. So how do I want to say this? And another thing is like the 216 is just 6 cubed. That's going to be important because we're going to take a cube root. So all right. Yeah, and another thing is I'm not sure if we emphasize exponential notation or cis notation, but oh no, not 3 power negative 3. Okay, so I'll do it like this. We do have this as a solution, but we also have multiple revolutions of the unit circle as a solution. Equivalently, we could write this in cis notation as this, and then cis, and then the angle. So this would be 3 pi over 2 plus 2 pi k. And then by Domau's formula, when we want to take the cube root of this, what happens is 216i cube root of this. What happens is that for complex numbers, the radius ends up being rooted. The power gets applied to the root, and so you end up taking a cube root of the radius. But then for the angle, that something also happens to the angle. The angle gets divided by the power, or multiplied technically. It gets multiplied by the power. Because the power we're using is actually a 1/3 power, we end up multiplying by 1/3, aka we end up dividing by 3 the angle. So if I'm using the two different notations simultaneously, I'm either in the exponential notation, I divide this by 3, I get pi over 2 plus 2 pi over 3k. If you prefer the cis notation, it's going to be basically the same thing. We just lower that exponent. Plus 2 pi over 3k, right? We just take that angle and we divide it by 3. And we end up with either of these formats. I guess at this point, using the cis notation would be easier because the next thing to do is actually to write this in what's called standard form for a complex number, this a plus bi kind of expression. From the cis notation, we know that expanding what that is out, it's cosine of the angle plus sine of the angle. And oh, there's one other little caveat here. This k value, it's going to repeat after a certain number of steps. So we actually only need it for these values, 0, 1, and 2. 0 is going to give us our principal root. 1 and 2 are going to give us our other roots. But then once we go beyond this, it's actually just going to cycle back. Okay. So, right, now expanding cis notation out, it's 2 pi over 3k plus I sine of pi over 2 plus 2 pi over 3k. And then all of this is multiplied by 6. Now, yeah. And again, we're going to plug in for k equals 0, 1, and 2. Which is kind of annoying. I'll show you how to do it. Okay, so 6. I don't know if this can handle complex numbers actually. And maybe some people's calculators can handle complex numbers. So, but let's just not do that. So 6 times cosine of pi over 2 plus 2 pi over 3 times 0. Fine. Oh, but that's not good. That's not good. I want exact. I probably do want exact, don't I? It doesn't say it, but I would prefer exact. Okay. All right, fine. I'll just do it manually. For k equals 0, we get cosine of pi over 2 plus I sine of pi over 2. This is for k equals 0. And where do I want to write this? I don't want to write this here. Okay, fine. 6 times cosine of pi over 2, you'd probably think about the unit circle. Pi is here, pi over 2 is this point here. Cosine is the x-coordinate, which is 0. So 0 plus I sine of pi over 2 is going to be 1. But you have an I in front of it. So you end up with 6I as this solution. Why did it? Oh, because it's in degree mode. Okay. Well, but some of them are going to give you square roots, so you have to, it's still probably necessary to do this a little bit by hand, unless your calculator is smart enough to give you root 3 as root 3 instead of 1.7 something. Alright, so this would be k equals 0 solution, the k equals 1 solution, so I'll put like, I guess, comma, and then this is like for k equals 0, this is for k equals 1, make this actually look legible, k equals 0, so this is one of the solutions. For k equals 1, we would have cosine of pi over 2 plus 2 pi over 3, plus I sine pi over 2 plus 2 pi over 3. Okay, so what angle is this? What is pi over 2 plus 2 pi over 3? That's going to be 3 pi plus 4 pi over 6. So we get 7 pi over 6. It's definitely a 30-degree angle, 157, so it's going to be 30-degree angle in the third quadrant. If you didn't know that, this is a unit circle thing. So this is, you would look at, oh, come on. You would look at this diagram and look for, or this table and look for 7 pi over 6, and you see it here. Because, I mean, you expect it to be 30-degree angle because the denominator is 6, and it turns out it's in the third quadrant. So, okay, how does this help us? Well, cosine and sine, we know that the angle, we know what values cosine and sine take on a 30-degree angle. So cosine of a 30-degree angle is going to be root 3 over 2 with a plus or minus. That depends on what quadrant we're in. Let's think about the quadrant. So the fact that it's over here in the third quadrant, actually both sine and cosine are negative, so this is going to be negative. And then it's going to be times a negative. Sine of a 30-degree angle is 1/2. So we end up with this. And if you didn't know those special values, that would be this other table over here. Right? So we're talking about a 30-degree angle, so we're talking about one of these guys. And you see that sine of a 30-degree angle is 1/2, cosine of a 30-degree angle is root 3 over 2. Okay. And yeah, the negatives are coming from the quadrant that we're in, and we would go ahead and simplify this. So we get negative 3 root 3 minus 3i. This is our solution for k equals 1. And then we have a third solution for k equals 2. So this one we would have cosine of pi over 2 plus, this time 4 pi over 3. I'm plugging k equals 2 into this expression now. And then plus I sine of pi over 2 plus 4 pi over 3. Okay. And let's see what this angle is. So 2 pi over 2 plus 4 pi over 3. 3 pi plus 8 pi over 6. When I get a common denominator, 11 pi over 6, 15711 tells me that this is in the fourth quadrant. Which, if you didn't know, 15711, that's 30-degree angle, fourth quadrant, right? The denominator of 6 tells us it's a 30-degree angle. Okay. Right. So, that means the values are the same. Cosine of a 30-degree angle is root 3 over 2. Sine of a 30-degree angle is 1/2. The only question is, are we dealing with pluses or minuses? So in this quadrant, cosine here, sine there. Cosine is positive, and sine is negative. So we have this, and this is a big multiplication symbol. That plus is redundant, and it looks kind of bad, so I'll just get rid of that. these are like sub cases. I don't know how you want to write this neatly, but yeah. Okay, and then we multiply the 6 across, and we distribute the 6. The minus gets picked up, so we get minus 3i as the third answer. Let me just check. Yes. Good. So I got that previously. Okay, and let's go ahead and box our answer. So what we found was we found three cube roots to the number negative 216i. And I guess one thing you could do just to like sanity check this, if your calculator supports imaginary numbers, does this really not support? I'm surprised that this doesn't. This should. Complex format, Cartesian, that's fine. Yeah, there has to be a way. How do you complex J engineers? Yeah, in some fields, people use J to be the complex number. Like Python does this as well. What? 3J. Uh-oh. What am I doing wrong? Settings, behavior, enable complex. Settings, behavior. Okay. I guess it's because otherwise like J is a variable. So then J now is a special number. Cool. So the way we would do this is we could just double check by raising it to the third power, right? Supposedly we calculated cube roots, so if we cube it, we should get back to the original. 6i, if we raise it to the third power, or no, not ij, j, 6j, because that's I need parentheses because otherwise the calculator doesn't know I'm also cubing the 6. So we get negative 216j, which is negative 216i. That's the original thing, so that one's correct. Minus 3 square root 3 minus 3j cubed. I need to specify square root of the value 3. Okay, good. And then the last one is just with a positive in front. And again, you also get minus 216j. So definitely the TI-84 has this stuff, so I expect the higher TIs to have this. I'm sure Casio also has complex numbers. Pretty much all scientific calculators should have some way of doing complex numbers. If you care to like double check your work, you can do this kind of strategy. Okay, and that is the whole practice exam. So I guess I'm gonna end it here.